The ocean was not always salty. For millions of years it was something else, something quieter, stranger. And the way it changed never really stopped. The water would have looked strange to you, darker, perhaps, warmer in some places than the warmest bath you have ever known. The sky above it would have been the wrong color, a hazy reddish-orange, no blue at all. The sun dimmer through an atmosphere thick with gases your lungs could not have used. Methane, carbon dioxide, ammonia drifting at the edges. Before you settle in, take a moment to like the video and subscribe, if you're enjoying these calm documentaries. I'd also love to know where you're listening from tonight and what time it is there, so feel free to leave a comment. There's something quietly comforting about knowing people all over the world are drifting through the wonders of Earth together. And then, the water itself. Real water. H2O. Molecules that had been falling from the sky for millions of years in the form of rain, collecting in the low places of a planet that was still figuring itself out. But it was not the ocean you know. Not yet. It was younger than that. And crucially, it was not salty. Or at least not very. Somewhere between fresh and what we would call brackish today, the earliest ocean sat quietly in the dark, waiting for what the land would give it. And what the land gave it, over millions and then billions of years, was everything. This is the story of how an ocean learned what it was made of. Take a slow breath. Let your body settle into wherever you are resting. Like we have a long time ahead of us and know where we need to be. The ocean has been patient for 4 billion years. Tonight, we can afford to be patient too. Close your eyes if that feels right. And let us begin at the beginning, which, like most beginnings, was also a kind of ending. The planet Earth had just formed. 4.5 billion years ago, give or take. A cloud of gas and dust collapsed inward under its own gravity, and what remained was a rocky body orbiting a young star. For a long time after that, the surface of the Earth was molten, a churning sea of magma, not water. The heat from formation, the constant bombardment of asteroids and comets, kept the entire surface liquid and glowing. This is called the Hadean period, named after Hades, the Greek word for the underworld. It was not a gentle time, but slowly, as the bombardment tapered off, as the surface began to cool, something remarkable happened. Steam that had been trapped in the atmosphere began to condense. And it rained. Not for a day or a week. For millions of years, it rained. Water fell from a sky that was always clouded, always roiling, and it pooled in the low places of a cooling crust. That is where the ocean came from. Partly from the sky, water vapor that had outgassed from the molten rock as it cooled. Partly from space, comets and water-rich asteroids delivering ice that melted on impact. The ocean did not begin all at once. It crept in from everywhere, finding its level, filling basins that had formed as the crust buckled and shifted, and for a while that water was relatively clean. Not pure. The volcanic outgassing had already loaded it with dissolved gases, with carbon dioxide that made it mildly acidic, with the chemical signatures of a planet in upheaval. But it was not yet the salt sea we know. For that, we need to turn our attention to the land. Every river that has ever run across the surface of this earth has been a kind of message, a slow, patient message, written in minerals and ions and dissolved rock, addressed to the ocean, taking sometimes thousands of years to arrive. Rain falls from clouds. It lands on mountains, on plains, on volcanic hillsides, on ancient granite ridges that have been standing since before the dinosaurs. And as it falls, as it runs across the land and gathers itself into streams and then into rivers, it does what water always does to rock. It takes things. Water is an extraordinary solvent. Not the most powerful one that chemistry can produce, but perhaps the most consequential, because it is everywhere, because it moves, because it is patient in a way that very few forces in nature are patient. A single water molecule, so tumbling over a granite surface, can pry loose atoms of sodium, calcium, magnesium, potassium, elements that are bound up in the crystal structure of the rock, but not bound tightly enough to resist water over a long enough time. This process is called chemical weathering. The rain dissolves the rock very slowly, imperceptibly slowly, on any scale that a human life can perceive. But on geological timescales, millions of years, tens of millions, it adds up to something staggering. The dissolved minerals travel with the water, down from the mountains across the floodplains, through the deltas where fresh water meets salt, and out into the sea. There, something happens that is both simple and profound. The water evaporates. The sun pulls it back up into the sky. But the minerals, the sodium, the chloride, the magnesium, and the sulfate, they do not evaporate. They have nowhere to go. They stay in the ocean, and the next river brings more, and the next rainfall after that, and the next across millions of years. This is the central secret of why the ocean is salty. The ocean is a place where minerals arrive and cannot leave. Water gets in. Water gets out. The water cycle is one of the great circular systems of this planet. Evaporation from the ocean, condensation in clouds, rainfall on land flow back to the sea. But the salt that the rivers carry, that stays. It accumulates. It has been accumulating since the first rivers began to run. Breathe slowly. Let that idea settle. The ocean is not salty because it started salty. It became salty, grain by grain, molecule by molecule, river load by river load, over a span of time so vast it resists imagination. Think of the Mississippi River, which carries roughly 136 million tons of dissolved minerals into the Gulf of Mexico every single year. Think of the Amazon, the Congo, the Ganges, the Yangtze, each of them running without pause every year, carrying their chemical freight from the mountains to the sea. Then think about how long they have been doing this. Not for 100 years, not for 1,000, for hundreds of millions of years. The salt in the ocean is the accumulated gift of every raindrop that ever fell on every mountain that ever rose from the surface of this planet. There is something almost unbearably patient about that. Something that, if you let yourself feel it properly, is rather comforting. The Earth has been working on this project for longer than we can truly conceive, and it is still working. Right now, as you rest here, rivers are moving toward the sea. Somewhere, a drop of rain is dissolving a grain of feldspar. Somewhere, a river is carrying the future salt of an ocean toward a coastline. It does not hurry. It does not need to. But rivers are only half the story. Beneath the ocean floor, the Earth has its own system of contribution, one that runs on pressure and heat rather than gravity and rain. And it has been adding salt to the sea in a very different way. The ocean floor is not a static place. It never has been. The great tectonic plates of the Earth's crust are always moving, always spreading apart at the mid-ocean ridges, those long underwater mountain ranges that run down the centers of the ocean basins like seams on a great dark quilt. At these ridges, magma wells up from below. New crust is born, and as the hot rock pushes up through the seafloor, it creates what geologists call hydrothermal vents, places where seawater seeps down into cracks in the ocean floor, gets superheated by the magma below, and then rushes back up through the vent in dark plumes of hot, mineral-rich water. These vents have been called black smokers because the plumes look like thick, dark smoke rising from the seafloor, though what looks like smoke is actually clouds of tiny mineral particles precipitating out of the superheated water as it meets the cold, deep ocean. The chemistry that happens at hydrothermal vents is complicated and beautiful and has a profound effect on the composition of seawater. Some elements are added. The hot water dissolves minerals from the hot rock and carries them up into the ocean: iron, manganese, zinc, copper, and others. Some elements are removed. The hot seawater reacts with the basalt of the ocean floor, stripping out magnesium and sulfate and exchanging them for calcium. Over geological time, this circulation has shaped the chemistry of the ocean just as surely as the rivers have. The ocean is not just the recipient of what rivers bring. It is also constantly being filtered and altered by its own floor, by the slow breathing of the Earth's interior. Let your breath slow a little more, in and out. The Earth breathes too, though on a time scale measured in millions of years. The mid-ocean ridges exhale. The subduction zones inhale, pulling old sea floor back into the mantle. And in between, the ocean sits, complex, chemical, alive in ways that are not biological but are no less intricate. There is another piece of this story that deserves a moment of quiet attention. In the very early history of the ocean, the chemistry of the water was profoundly different from today. The early Earth had far more volcanic activity. The ocean floor was spreading faster. Hydrothermal circulation was more intense, and the composition of the atmosphere, which interacts with the ocean constantly, exchanging gases dissolving into the surface layer, was radically different. The early ocean was likely more acidic, rich in iron, perhaps rich in silica. The concentrations of various minerals were not what they are today. The ocean has not simply accumulated salt steadily over time. It has changed in character, been reset by catastrophes, adjusted by the evolution of life, unshaped by events that had nothing to do with chemistry and everything to do with biology, because life, when it arrived, changed everything. Every drop of ocean water you see today has been recycled countless times over billions of years. Sometime between 3 and 4 billion years ago, in conditions that scientists are still working to understand precisely, life began in the ocean. Not complex life. Not anything with eyes or fins or the ability to feel the current. Single-celled organisms, simple, small, chemically inventive, that found ways to use the molecules around them to power their own existence. Some of them used hydrogen sulfide from hydrothermal vents. Some of them found ways to capture energy from chemical gradients, from the difference in charge between the inside and the outside of their membranes. And, eventually, and this is one of the most consequential events in the history of this planet, some of them learned to use sunlight. Photosynthesis, the capture of solar energy and its conversion into chemical energy, with oxygen released as a byproduct. when cyanobacteria evolved the ability to photosynthesize, roughly 2.5 billion years ago, they began doing something that would change the ocean, the atmosphere, and the course of life on Earth. They began flooding the world with oxygen. This event is called the Great Oxidation Event. And it was, in many ways, a catastrophe for the life that had existed before it. Organisms that had evolved in an oxygen-free world suddenly found themselves in an environment increasingly hostile to them. But for the oxygen-tolerant organisms that survived and adapted, it opened up an entirely new world of metabolic possibility. What does this have to do with salt? Everything, and nothing, and everything again. The life that evolved in the ocean over billions of years became one of the most powerful forces shaping the chemistry of seawater. Tiny organisms called coccolithophores, single-celled algae, build their shells from calcium carbonate, pulling calcium out of the water. When they die, they sink to the seafloor, taking their calcium with them. Over geological time, this biological pump has moved enormous quantities of calcium out of the ocean and into the sedimentary rock of the ocean floor. Coral reefs do something similar. So do shellfish and sea urchins and the enormous diversity of organisms that build themselves from minerals dissolved in seawater. Life is not just a passenger in the ocean. Life is a geochemical force. The diatoms pull silicon out of the water to build their beautiful glass shells, and the foraminifera pull out more calcium. The ocean, over billions of years, has been selectively depleted of some minerals and enriched in others, not just by geological processes, but by the patient, ceaseless chemistry of living things. This is why the ocean's composition today is what it is. Sodium chloride, common salt, makes up the majority of the dissolved minerals in seawater. Not because it is the most abundant mineral in the Earth's crust, but because it is the one that life has been least interested in consuming. Calcium gets locked into shells. Silica gets locked into diatom frustules. But sodium and chloride, they accumulate. They stay in solution. Life does not find them particularly useful in large quantities. So the ocean gradually became a sodium chloride solution. Not because that was inevitable. Not because that was the only possible outcome, but because of the particular intersection of geology and biology and chemistry that happened to characterize this specific planet over the last 4 billion years. Breathe. Feel the weight of that. The ocean's saltiness is not an accident, but it is also not simple. It is the outcome of an almost incomprehensible number of interactions, played out over a span of time that makes human history look like a heartbeat. And it is still changing, slowly, imperceptibly, but still. But one of the remarkable things about the modern ocean, and by modern I mean the last few 100 million years, is that its salinity has been roughly stable. Not exactly. Not perfectly. There have been periods when the ocean was slightly saltier, slightly fresher. There have been ice ages when so much water was locked up in glaciers that the ocean shrank and its salinity crept upward. There have been warmer periods when the glaciers melted and the fresh water returned, diluting the salt. But in general, the ocean has maintained a salinity of roughly 35 grams of dissolved minerals per kilogram of seawater, 3.5%, for an impressively long time. And the reason for this stability is one of the most elegant things in geochemistry. The ocean is in a kind of balance. Input roughly equals output. Rivers bring minerals in. But minerals also leave the ocean in several ways. Some are precipitated out as chemical sediments, calcium carbonate, silica, iron oxides, when the water becomes saturated. Some are incorporated into the shells of organisms that eventually sink to the seafloor and become sedimentary rock. Some are removed by hydrothermal circulation, as seawater reacts with the basalt of the spreading ridges, and some are removed when seawater gets trapped in evaporate basins, shallow seas that dry up and leave behind thick deposits of salt, like the salt flats of the American West or the great salt deposits that underlie much of the Michigan Basin. This is called geochemical cycling, and it is one of the great self-regulating systems of the Earth. The planet is not passively accumulating salt without limit, and it is cycling minerals through a series of reservoirs, rock to river to ocean to sea floor to subducted crust to volcanic eruption to rock again, in a loop that operates over timescales of millions to hundreds of millions of years. The ocean participates in this loop as both a sink and a source. It receives minerals from rivers and hydrothermal vents. It returns minerals to the sedimentary rock that eventually gets subducted back into the mantle. The mantle, over geologic time, releases those minerals back to the surface through volcanic activity, and the cycle continues. This is the deep breath of the Earth, a respiratory cycle measured not in seconds, but in eons, and the ocean is the lung. Somewhere, right now in the Pacific, hydrothermal water is rising through a black smoker, carrying iron and manganese and heat from the mantle below. Somewhere in the Atlantic, a river is depositing its mineral load into an estuary where fresh water mixes with salt in a gradient of chemical complexity. Somewhere in a lab, a geochemist is measuring the ratio of strontium isotopes in a piece of ancient limestone, using it to infer the salinity of an ocean that existed before the dinosaurs. And here you are, resting, breathing, carried by a planet that has been doing all of this without pause for 4 billion years. Let that feel like what it is, a kind of support. Not sentimental, simply factual. You are resting on a world that has been at work for longer than the mind can truly hold. And somehow, in all that time, it has kept the ocean roughly salty enough, roughly warm enough, roughly hospitable enough for the unbroken chain of life that eventually led to you. The margin for error over that span of time was narrow, and yet here we are. It is worth pausing in the quiet of this moment to consider that Earth may not be the only world with a salty ocean. Europa, one of Jupiter's moons, slightly smaller than our own moon, is covered in a shell of ice. Beneath that ice, scientists believe, there is a liquid water ocean perhaps 100 kilometers deep. The evidence is compelling. The surface of Europa is crisscrossed with fractures that look like the patterns you see when ice shifts over water, and the moon's magnetic field shows the signature of a conductive fluid beneath the surface. Is Europa's ocean salty? Almost certainly, though the chemistry may be different from Earth's. The heat that keeps it liquid does not come from the sun. Europa is too far away for that. It comes from tidal flexing. It's the gravitational kneading of the moon as it orbits Jupiter and is pulled and compressed by the giant planet's gravity. That same tidal heating may drive hydrothermal activity on Europa's seafloor. If it does, if there are hydrothermal vents on the floor of Europa's buried ocean, then the same processes that have shaped the chemistry of Earth's seas may be happening there too, right now, in the dark beneath kilometers of ice. Enceladus, a moon of Saturn, is even more tantalizing. It actively vents water vapor and ice particles into space from cracks at its south pole. Geysers driven by the liquid ocean beneath. The water that has been analyzed from these geysers contains sodium chloride. Salt. The same salt that fills our ocean, carried upward from a moon that orbits a planet 1 billion kilometers from the sun. And the chemistry of salt water may be in some sense a universal feature of rocky, water-bearing worlds with geological activity. The same forces, volcanism, chemical weathering, the solvent power of water, may be at work across the solar system and perhaps across the galaxy. The ocean is not just an earthly thing, it is a planetary thing, a consequence of rock and water and time, and that means the question of how our ocean became salty is not just a question about our world. It is a question about what happens when water and rock and heat and time are brought together anywhere in the universe. It is a question with implications we have barely begun to explore. Lie still for a moment. Let the darkness behind your eyes expand outward, past the ceiling, past the sky, past the atmosphere, past the orbit of the moon, out into the cold spaces where other moons circle other worlds with their hidden seas. Salt water, or something like it, may be one of the most common substances in the universe. And we swim in it, we came from it. Every cell in your body still carries, in its internal fluid, a chemical memory of the sea, a saline solution that is in its basic character not unlike the ocean that life first evolved in billions of years ago. You carry the sea with you. In you, you always have. There is an old observation in biology, not a law exactly, but a pattern that holds with remarkable consistency, that the internal fluids of marine invertebrates are remarkably similar in composition to seawater. This is not a coincidence. Life evolved in the ocean. The first cells developed their internal chemistry in close relationship with the water that surrounded them. And as life gradually moved from the sea to freshwater, and from freshwater onto land, it carried its internal sea with it, the fluid between your cells, the interstitial fluid that bathes every tissue in your body, contains sodium, potassium, chloride, calcium, magnesium, the same ions that float in the ocean. Your blood plasma is salty. Your tears are salty. The fluid in your inner ear, which helps you maintain balance, is salty. You are, in a very real biochemical sense, a container for a small piece of ancient seawater. The concentration is different. Your body regulates it carefully, keeping it at a salinity lower than the modern ocean, closer to what scientists believe the early ocean may have been when the first animal ancestors were evolving. But the chemistry is unmistakably maritime. When you cry, you are crying salt water. When you sweat, you are sweating salt water. When you bleed, your blood carries the ionic signature of a sea that existed hundreds of millions of years ago. There's something profound in this that does not require any mysticism to appreciate. We are creatures of the ocean, regardless of where we live. The ocean is not outside us. It is the template from which our bodies were built, and the chemical environment that shaped every metabolic process we depend on, the ancient home that every one of our cells still, in some sense, believes it is living in. The rivers carried minerals to the sea. Life evolved in that mineral-rich water. Life eventually crawled out onto land, and it brought the sea with it, tucked inside its cells, carried forward through hundreds of millions of years of evolution. You are the ocean's memory of itself. Rest with that for a moment. Your breathing slows. Your muscles settle. The weight of your body sinks gently into whatever is beneath you. And somewhere in your bloodstream, sodium ions are moving through channels in cell membranes, creating the electrical gradients that allow your heart to beat and your neurons to fire and your lungs to breathe. Salt. Ancient, accumulated, river-carried, volcano-leached, life-preserved salt. You are made of it. You depend on it. You are, right now, running on it. We have traveled a long way tonight. From the molten surface of the early Earth, where the first rains were beginning to fall on cooling rock, through the first formation of the ocean, vast and warm and strange, through the long, slow work of rivers carrying their mineral messages from the mountains to the sea, through the volcanic breath of the mid-ocean ridges, adding their contribution from below, through the rise of life, which took the chemistry of the ocean and turned it into the chemistry of a biosphere, through the steady state, the elegant balance between input and output that has kept the ocean's salinity roughly stable for hundreds of millions of years, through the tantalizing suggestion that other worlds, in the dark beyond our sky, may have their own salty seas, so following the same chemical logic on different planets around different stars, and through the startling, grounding realization that the ocean did not stay outside us, that we carry it with us, in our blood, in our tears, in the fluid that surrounds every cell of every tissue of every organ that allows us to be alive. The ocean became salty over millions of years, over billions of years, through a process that was never directed by anything, never aimed at any particular outcome, never in any hurry. Rain fell, rock dissolved, rivers ran, minerals accumulated, life evolved. And out of all that patient, unguided, unhurried chemistry, an ocean emerged that was exactly salty enough to allow the kind of life that eventually became us. There is a word for this kind of result. Not a scientific word, but a human one. The word is gift, though no one gave it. It simply emerged from time and chemistry and the particular conditions of this particular planet over a span of time so long that human language barely has the tools to describe it. You are resting now. Your breath is slow. The thoughts that were moving through your mind when you lay down have probably softened, drifted, begun to dissolve at their edges the way salt dissolves in water, completely, invisibly, until you can no longer find the boundary between one thing and another. That is a good place to be. The ocean does not sleep exactly, but at its greatest depths, below the reach of sunlight, below the thermocline, in the abyssal plain where the pressure is enough to crush anything that did not evolve to withstand it, the water is cold and very dark and very still. The currents move there, but slowly. So slowly that a parcel of water at the bottom of the deep Pacific may not have seen the surface in 1,000 years. In that stillness, in that darkness, in that cold, the ancient water sits, carrying its salt, carrying the chemical record of 1 billion years of rivers and volcanoes and living things, carrying, somewhere in its dissolved ions, the atoms that were once part of a mountain that no longer exists, and before that a volcanic ash cloud, and before that the mantle of the early earth, and before that a cloud of gas and dust that collapsed under its own gravity to form this world. Everything cycles, everything returns. Nothing is truly lost, only changed in form, moved from one reservoir to another. transformed by time and chemistry into something new. As the salt in the ocean tonight is the same salt that the earliest rivers carried. It has moved through rock and water and living things and back again. It has been part of shells and bones and ancient seafloors and the blood of creatures that no longer exist. It will be part of more things still, after the ocean as we know it is long gone, and the continents have moved, and the sun has changed, and the world is different in ways we cannot predict. But right now, tonight, it is simply floating in a dark sea, patient, ancient, salt, and you are drifting toward sleep. Let the thoughts go now. Let the images dissolve. The early ocean, the black smokers, the rivers carrying their freight of dissolved rock, the tiny organisms building their calcium shells. Let all of it drift away, like sediment settling toward the seafloor. There is nothing you need to hold on to tonight. The ocean has been here for 4 billion years. It will be here when you wake up. The rivers are still running. The mid-ocean ridges are still breathing. Somewhere, a river is carrying a grain of sodium toward the sea. And you are safe, and still, and resting. Sleep well.